Hi, everybody. Here is a little supplement on the solution to assignment 2, which you can find on our website. So the first part was to take that temperature signal and do a little Fourier analysis on it. And of course, the whole point of doing the Fourier analysis is to try to kind of extract the critical cyclic components embedded in the data. Okay. Um, so if we take that Fourier transform and notice that I've only plotted it up to the halfway point because everything beyond that is redundant. Okay. And so again, you do not have to plot the whole thing. If it makes a better presentation to plot only half of it or even less than half of it, if there's stuff you don't need to show, that's okay. All right. In fact, that's good technical communication practice, right? That's the way we should present graphs. Secondly, graphs should always be labeled. And for our purposes, again, the y-axis is always variable. You can put things like magnitude or magnitude squared or signal power, if that's appropriate, signal magnitude, something like that, right? Because we don't always really know the units there. But the frequency axis is going to be very critical kind of all the time in this course, okay? So do pay attention to that. Now, when we take the Fourier transform of this in MATLAB using the FFT function, we get something like this, and I have plotted it in terms of the MATLAB index. So the first element is element 1, because of the way MATLAB does things, which again is not great, but that's the convention that they chose, okay? And then we kind of go from there. Okay. Now, the first thing to recognize, of course, is that element 1 is 0 frequency, which is the DC term, the average value of the signal. And since this is a temperature signal, you know, it averages around 40-something degrees and varies around that. We don't really care about that one, okay? Because that's just the average value of the signal, right? When we're interested in the kind of embedded cycles in this, we're looking at things of higher frequency. This is frequency 0, okay? Frequency 1, frequency 2. Now, what units are those? Okay, remember that the MATLAB index, if we subtract 1 from the MATLAB index, we get the number of cycles in the recording time of the signal, okay? This signal is recorded over 48 hours. So MATLAB index 3 is 2 cycles in 48 hours. And in a, you know, for purposes of presenting it in a more meaningful way, a way that's more accessible to the reader, it's probably best to state that, oh, that's a 24-hour cycle. Okay. The next highest one is 6 cycles in 48 hours, MATLAB index 7. And so that's an 8-hour cycle. Okay. And then the next highest one is a 12-hour cycle. And you'll recall this was like 12 hours on, 12 hours off with the light in this experiment. So, you know, the 24 and the 12 could actually be associated with the external stimulus of the lights going on and off, right? But this is not synchronized with the lights going on and off. And so the kind of hypothesis generated by that is that this is an internal cycle, a circadian rhythm cycle that isn't affected by the external lights on, lights off cycle. Okay. And then there's the next highest one is this guy here, which is about 4.8 hours, I think. Okay. So the key thing here and the key skill to get out of this is converting these frequencies, okay? Now, since the time scale is hours, this is not hertz, okay? Remember, hertz is only cycles per second. and it's not meaningful to express this in terms of hertz because you get like some very tiny number in cycles per second. Okay, and so expressing things in a meaningful way, again, is technical communication, right? And so that's important, and that's the thing I try to emphasize here. So label your graphs, give the units on your graphs. If it's MATLAB index, you can plot it that way, but it's good to indicate something like this to show what it really means in terms of the real world. And then, learning to translate these into real world frequencies is an important skill that we're kind of emphasizing here. And we're going to use it all through the course. Okay, so that's important. Let me just try to reinforce that just a little bit here by pointing out that, okay, if we do an FFT and we plot that, okay, and we just do, plot the absolute value FFT, then it's going to give us an x-axis, which is the MATLAB index, and that's going to go from 1 to n, where n is the size of your signal, however many time samples are in your signal. Okay, so that's the MATLAB index scale. Now, in terms of cycles per recording period, whoops, sorry about that. The scale goes from 0 to n minus 1. Okay, and again, the halfway point, right, is basically anything after that is redundant and shouldn't be interpreted as any particular, as a frequency, from here. It is the kind of negative side and so forth. So, for example, if you were going through this and processing it and you found, okay, the halfway point is 125 hertz, then up here is not really 250 hertz, right? The halfway point is the highest frequency that is truly meaningful and that you can represent in that situation. And anything above that is kind of false. Again, that's a thing we'll explain later, right? So, but understand that. So that's redundant and kind of false. All right. All right, so if we make it cycles per recording period, then we have that. And so then the idea to get to cycles per second would be to take this and multiply it. Let me borrow that. We'll go there, right? And basically take that times one recording period, and we'll call it capital T seconds, right? So basically dividing by the recording period, and so that will give us a scale that goes from 0, well, up to here, n minus 1 over t. And of course, this is, roughly n over 2 t. Okay. So if you want to go to, and again, cycles per second wouldn't be appropriate for that first problem, but whatever the length of the recording period is, that's how we're going to get that conversion. Okay. So do keep that in mind because, again, I kind of expect you to, and we want to interpret those frequency scales in terms of meaningful real world kind of units in many cases. Okay. Back to the solution. All right. And the other point in relating this to the example I did, where we fit a couple of sinusoids to the data, subtracted to get the error, and then kind of went to the, took that residual error and then fit another sinusoid to it, is the ones we fit were the average value, we fit the 2-cycle one, we fit the 6-cycle one, okay? And then we subtracted that off, and then if we had taken what was left and somehow decided that we were going to fit this one in, we could have done that, and again, fit that to the remaining error, subtract it to get what's left, and basically everything that's left is, if all combined, you know, would basically make up these other cycles. One more thing, this is a case where it's much more meaningful to use a semi-log plot, because then you can see these different cycles much more effectively, okay? Because if you do a linear plot, it's dominated by this guy, and this is a guy we don't care about, okay? And so this is a situation where semi-log plot. Now, this is again a part of technical communication. You can use a linear plot, you can use a semi-log plot. In different situations, you know, one is going to be the appropriate one, or the other one is going to be the appropriate one. And one of the skills you need to have is choosing the right kind of plot, okay, that makes your point. When you make a plot like this, you're telling a story, and you're trying to present information that supports what you describe in your little discussion, as I have down below, okay? And so choose the scale that communicates your information the best, okay? You'll find I do, you know, I mark off a couple of points if your graph is not communicating properly, okay? So pay attention to that. All right. Moving on to the second part was statistics of 2 signals. And basically, you know, so a lot of this is just running through, doing some MATLAB stuff. When it comes to the histograms, again, for presenting this properly and making a good visual comparison, you really have to set it up so that the bins are the same width for both histograms. Otherwise, you're plotting, you know, one where the bins are very narrow, along with another one where the bins are very wide, and it just doesn't create a meaningful comparison. So if you know, do it this way, and look at MATLAB help files, right? One of the things I'm always saying is don't just rely on the default behavior of a MATLAB function. You can manipulate them in a lot of ways, and so there are ways, for example, to get both of these histograms with the same bins, okay? And doing that makes a much better, more meaningful comparison. So you see that EMGFX is much more narrow and more highly peaked in the center versus EMG, which is not as high in the center and wider, okay? This is a filtered version of this. And so what does the filter do? Well, it kind of reduces the variation. When you look at the variance, you see that, okay? And that's frequently a reason why we use low pass filters, is to reduce the variation. Normal distribution, you could answer that either way. You can say, yeah, I mean, you know, it's sort of like a bell curve, so you could justify using a normal distribution, or you might say, no, you know, it might be a little too peaky, or something that, you know, or these long tails might not represent a normal distribution very well. And basically what I'm looking for is that, you know, it sort of shows in your answer that you kind of understand what a normal distribution is, okay? So you could answer that either way if justified. I say, yeah, they're actually, it turns out if you actually try to fit them, it's not a great fit, but it's not terrible. So covariance, okay, this is an important point, right? We compute the covariance, which gives us the variances this way, and this is the covariance term in the off diagonal part. And the key thing, right, is, okay, that's positive, sure. Which might indicate a relationship, but you must always consider the covariance relative to the variances. If you just look at this number and say, oh, it's like 3.1 E5, That's a big number. So it must be a strong relationship. Well, no, because the variance is on the order of E7. Okay. Um, if you think about it, you know, if you took the same data and multiplied it all by 10, right? Multiplied every data point by 10, what would happen? Well, everything here would get, because these are all squared terms, right? Everything here would get scaled by 100. And then you say, oh, well, then that's 3E7 is the covariance. That's a much stronger relationship. Well, no, it's not going to be a stronger relationship if all you did was multiply it by a scalar. Okay, think about that. So it's always important to think about this relative to these guys. And I will probably do a little supplement to support that a little bit more. But if you look at this, right, this is 1 to 2 orders of magnitude below the variances. This can never exceed the variance of one of these, by the way. Okay. And so it's pretty small relative to these guys. So we would say maybe a relationship, but very weak. And you might, if that weak, you might be justified in considering them to be independent of one another, which seems counterintuitive, okay? Because they, you know, this, or fx is a filtered version of this. So it seems like there should be a relationship, but there is a catch to that we're going to explain next time we meet. Okay. Sleep data. So we're comparing an EOG and an EEG, and this is real human data taken at UNC Sleep Clinic. Again, I want you to be a little curious and explore a little bit. Sometimes you're going to have to plot things on, you know, both a semi-log and a linear scale in order to get the whole picture of the data. So don't just take the first plot you have. You need to explore a little bit. So if you know, if you don't zoom in this plot or use a, you know, semi-log on the x-axis, on the frequency axis, which you can do if it's appropriate, you kind of miss the details down low. And if you look at the information on EOG and EEG, the low frequencies are what's important, right? So cycles per 500 seconds plus 1. Again, I'm using the MATLAB index, although it's probably better to convert to Hertz, okay? But that says 1 Hertz is right here, okay? And this plot only goes up to 2 Hertz. If you look at information on these things, it's very low frequencies that they're interested in, below 1 Hertz, primarily. Definitely below 10 Hertz, or 15 maybe. And so the key distinction is, you know, yeah, they're kind of about the same at the upper end, but there are some significant differences down here at the lower end, right? And if I was to look at this is like, you know, 0.2 Hertz is right here, where this has a lot of activity. This is dropping off below that. And so that's the key difference between those two things. And you need, you know, again, you might need to explore a little bit to find that. You will probably get different numbers than me, but again, it's just a matter of, did you approach it appropriately? If you didn't look at this low end of the scale, then you might be missing some of the detail there. Okay. There's that high frequency spike, which turns out to be, if you do the right conversion, right, where the recording period is 500 seconds, 30,000 cycles, it's 60 cycles per second, which is AC power lines, which is a frequent problem that you should be aware of in medical instruments, because there's a lot of stuff plugged into the AC power lines, right? You know, in a hospital or other clinical environment, there's a lot of electricity going around. And so that commonly causes interference with these very sensitive sensors, right? So it's very common to have 60 cycle interference. And that's a thing you're often trying to filter out. So I'm sure that those of you who've taken instrumentation have, they've referred to that. Of course, if you didn't, again, if you got the conversion wrong, you would get some other frequency and it wouldn't be obvious that it's 60 cycles. Okay. The covariance, again, it's the same situation, right? Looking at the covariance term, it's again an order of magnitude below that, almost 2 orders of magnitude below that. It's pretty small, and there's not much relationship between the EOG and the EEG in this subject, and as a result, because the covariance term is small relative to the variances. Okay. That doesn't tell us the whole relationship, and this is a thing we're going to take up in the next class, because it only tells us the covariance of the two simultaneously, and they could still have a relationship sometime apart if one kind of leads the other or lags the other in terms of time. That is, an event happens in the EEG, and then a short time interval later, it happens in the EOG, and those are correlated. Well, this isn't going to reveal that, okay? Something else called the cross correlation that we will talk about next time will reveal that, okay? Okay, so that concludes my discussion of the homework, and look out for other supplemental recordings. Thanks. See you soon.